on superconductivity. The first speaker will be Mike Norman from Argonne National Lab. What's up?
Yep. Thanks, Eduardo. I thought I would start out with a few pictures. I don't think these are mine. I think they're actually David's. I liked it. These are from the Nobel thing back in 2003. That's a good one of you, Tony. That's pretty typical. He's talking to Alex. This is great. Eternally cheerful. Where did Claire go? Claire's not back yet? Oh, I couldn't resist. I had to sneak this one in, Claire. And then lastly is a great picture. I don't know, Dave was here earlier this morning with Dave, Bob, and David, which is nice. I feel I have to tell a story. So as David Merwin said this morning, it's a week-long thing. And maybe the best thing is at the end, the so-called St. Lucia Ball, which is put on by the students. It is supposed to be a dinner, but I think it's actually an excuse for consuming massive quantities of alcohol. As you remember, you got, the point is the students get out the award. What is the Order of the Ever Smiling and Jumping Little Green Frog Award? And to get this award, you have to answer a silly question and then jump up and down on the stage like a frog, right? And Tony's question, but I don't know if you remember, I remember. What do you get when you cross pasta with antipasta? Tony's answer, super pasta. So anyway, I'm going to be your tour guide on this rather baroque phase diagram, which is the phase diagram of whole doped cuprates. It reminds me of this commercial that Shaquille O'Neal did for Carnival Cruise Lines where they said he had 30 and he thought he meant he had 30 minutes. They said, no, you have 30 seconds to do the tour of the ship. Fortunately, I have 30 minutes, and we'll take you a little tour of this diagram and talk about some open questions. So in some sense, cuprates are actually relatively simple from an electronic structure perspective. You have x squared minus y squared copper orbitals hybridized with oxygen p orbitals. And this is what makes cuprates sort of unique. The oxygen p and copper d orbitals are almost degenerate. That means that you have a lot of covalency involved, and because of this, doped carriers typically are mobile because of the amount of oxygen admixture. And this is what makes cuprates different from other transition metal oxides, where you typically get polaron formation. And of course, Phil Anderson realized early on that you would have a half-fill band, and therefore, since the material he predicted was going to be an insulator, then you expect that something like the Mott Hubbard or the more modern variety charge transfer insulator would occur. Now, some of you might remember Phil also proposed that the stoichiometric material would be a quantum spin liquid. And of course, it turns out it's not. It's actually a garden variety antiferromagnet. And the antiferromagnetic ground state you see is actually not much different than what you see in other transition metal oxides. This compares lanthanum cuprate with lanthanum nickelate. And magnetic structure is almost identical. On the other hand, magnetism disappears very quickly upon doping. So after a few percent whole doping, the magnetism disappears, and then you have this marvelous superconducting phase. And as was alluded to this morning, there was a lot of debate about what the superconducting phase was, and then Tony suggested this experiment that was carried out by Dell with samples made by Don Ginsberg, and some analysis experiments were done by John Kirtley and Cheng Sui at IBM. And with this phase-sensitive tunneling, we know that we have a D-wave order parameter. It's actually quite spectacular because almost all other known materials, we really don't have a definitive understanding, at least in an unconventional case, what the order parameter is, except for this example and, of course, helium-3. And as far as we know, this is a pretty innocuous superconductor. It behaves BCS-like fashion. So if you look at the phase diagram, it's actually the superconducting phase, which is the least anomalous phase. And there's the phases that surround it, which are the most anomalous, which is of interest, right, because superconductivity is an instability of the normal state. if you want to understand the origin of the superconducting phase, you need to understand the origin of the normal phase from which it emerges. There are a few other things that we know, and one of them is that the D-wave pairs involve electrons on near-neighbor copper sites. The reason why we know this is that the angular dependence of the gap can be measured by, in this case, angle resolved photoemission, and it fits this formula cosine x minus cosine y, which is a Fourier transform of electrons sitting on near-neighbor copper sites. So that's important fact number one. And important fact number two is if you look at the normal state, say out in the antinodal region where the superconducting gap is largest, the normal state for most of the phase diagram is incoherent, but in the superconducting state you get coherence. And this is again a big difference from BCS theory where you go from a coherent normal state to a coherent superconducting state. Here over most of the phase diagram you go from an incoherent normal state to a coherent superconducting state. And you can use things like angle resolved photoemission. This is again out near the antinodal region of the Brillouin zone where the superconducting gap is largest, and you can map out as a function of doping and temperature that in this region of the phase diagram you actually have coherent excitations. So you have coherent excitations in the overdope phase and in the superconducting phase, but in the strange metal phase and in the pseudo gap region of the zone, you have evidence for non-Fermi liquid behavior in the normal state. And this behavior of the strange metal phase where you have no spectral gap but you actually have no coherent excitations was understood early on. These are transport measurements on single layer BISCO, rho versus temperature, and you can see the linear variation of temperature extending over decades of temperature. So this is very unusual, right? Because resistance going like an odd power of temperature is a rather unusual thing that typically happens maybe at higher temperatures. You can have this, say, electron-phone interaction when you go to high temperatures, but to have it persist all the way down to low temperatures is very unusual. The other unusual thing, of course, if you look at the C-axis resistance, is insulating. Material looks like it's going to be an actual in-plane metal and a C-axis insulator, and then at low temperatures you become superconducting and you establish coherence. And this linear T behavior is reflected in photoemission. So if you look at the omega and temperature dependence of the photoemission line width, this is exactly what you expect. Material is line width is linear in omega, and then then when you get down to frequencies below temperature, it saturates. So you see this saturation effect. And you also see this in optics. This is a rather famous paper done by the next speaker, Dirk van der Morel. And if you look at sigma of omega versus omega, you see these very strange power law behaviors indicating that the normal state is anomalous. And I don't want to dwell on this, but because Philip was one of the organizers, I had to sneak this in, that in fact there's this theory based on black holes in an ADS space, anti-de Sitter space, where basically you have some sort of a conformal field theory sitting on the boundary of the space-time, and as you go towards this black brane, which is the horizon of a black hole sitting in this ADS space, this dimension actually plays the role of a renormalization group flow. And based on these ideals, you get this concept of Planckian dynamics where the scattering rate goes like h over 2 by kt, which is more or less consistent with data that you see in the cuprates. And so this is ideal that this strange metal phase can be represented by black hole physics. Now, perhaps the most studied part of the phase diagram is this so-called pseudo gap region. So if you look at temperature versus doping, below some line here, which seems to be more of a crossover line than anything else, you start to see evidence for a large spectral gap opening up in probes like photoemission and optics. And there are various anomalies that occur across these lines or near to these lines that I'll talk about. And over most of the phase diagram, superconductivity emerges from the pseudo gap phase. And there's evidence for charge order and other things happening. And then eventually, at low doping, you have a metal insulator transition where you go from a superconducting phase to the antiferromagnet. And actually, if you look at the resistance near this boundary point, people like Dell have worked on this, you actually see the universal conductance value for pairs. So it looks like you're going from mobile Cooper pairs to localized Cooper pairs as you go across this phase point. So the pseudo gap phase was known for a long time. I think it was first explored by NMR data. So people like Charlie Slichter and some of his students worked on this. But at high temperatures, you see a susceptibility that's more or less flat in temperature and then at some magic temperature. Pointer's not working so great, but you can see at some temperature, the susceptibility starts to drop, which was sort of taken as evidence that either you were having antiferromagnetic spin fluctuations coming into play or that you had singlet formation, that is, the electrons or the carriers were starting to form singlet-type pairs and with a susceptibility that decreased. And this led to the possibility that people like Mohit Randeria and others talked about whether you actually had preformed pairs so that you may be sort of like what you see near Bose-Einstein condensation. And there's evidence for this. Photoemission data, of course, shows that large regions of the Brillouin zone are gapped out with an arc of excitations that typically shrink as you go down in temperature. But if you look at, say, optics data or Nernst data, there's also evidence that something that you could interpret in terms of preformed pairs cuts in at an onset temperature much higher than Tc. But of course, there are alternate interpretations of these data as well. And so there's a lot of debate whether, in fact, you have something like diamagnetism occurring. Certainly, you have a drop in the susceptibility that looks like diamagnetism, but the overall susceptibility still remains strongly paramagnetic. Evidence also was seen for time reversal symmetry breaking. This was an early proposal by Chandra Varma that you would have basically loop currents existing in the sample where the hopping matrix element would be complex, which would lead to time reversal breaking. There was a prediction by this, which was later seen by neutron scattering, and that signal more or less cuts on at the same so-called T star. And one way of interpreting this is that you had these loop currents like this, which were anti-phase from this copper site to the next, although there are potential alternate explanations involving magnetism on the oxygen sites as well. And even though you say, well, this was a long time ago, there's been some recent confirmation. Second harmonic generation, which can either detect time reversal or inversion breaking, cuts on at roughly the same temperature. And then there's been a recent experiment from muon, a mu-SR experiment. For a long time, muons were not seeing anything. But this latest muon experiment basically said they have an indication of internal magnetic fields setting on near a temperature of T star. So one of the more dramatic things was that charge order of some sort people suspected was playing a role in the phase diagram. Eduardo and his colleagues like Steve were earlier proponents of this. This really came to the forefront when STM developed to an extent where they could actually start seeing some very interesting effects. And this is an early experiment done by Jenny Hoffman when she was in Seamus Davis's group. And they looked at the halo around vortex core. So the vortex core itself is very small because these are small coherence-linked superconductors. But outside of this, they saw a halo that indicated some kind of checkerboard-type charge ordering occur. Then, about 5 years ago or so, people started doing both resin and hard X-ray scattering, and an effect that had been missed for a long time was seen that as you go below some temperature, below T star, but still well above Tc, you start to see charge correlations develop that look like they're going to diverge as you go to the zero temperature limit, but then when you hit Tc, they get suppressed. Of course, if you go up in a magnetic field, and suppress superconductivity, then these charge correlations come back. And this is some sort of short-range ordered phase that more or less sets in at a temperature well below T star, but well above Tc. What is now known is if you go to high magnetic fields, you actually get long-range charge order, which is interesting. This long-range charge order has the same in-plane wave vector as a short-range order, but it has a different out-of-plane wave vector. So the short-range order happens at L equal 1/2, and the long-range order happens at integer L. And this has been seen also by NMR experiments, and we know this is a thermodynamic transition. It's been seen by ultrasound. The interesting thing seen by STM, though, is that this is actually a D wave, has a D wave form factor. In some sense, this state is a particle-hole conjugate of the D-wave superconductor, in that if you look at the phase factor, so you have charge density wave going this way in orthogonal direction, they're out of phase by pi over 2 as you go from the x to the y direction, so they have a D-wave-like form factor. And so there's been a lot of theories about the relationship between this D-wave form factor and whether this is a particle-hole mirror image of the D-wave superconductor. And then most recently, there's been evidence from this preprint that came out a couple of months ago that in fact you might have so-called pair density wave state. That is a superconducting state which is modulated in space with a wave vector half of what you see in the charge order. And the speculation is that, one of the speculations is that in fact the charge order is secondary, and in fact the pair density wave state might be the primary order parameter, and the CDW state is just a secondary consequence of this. And there are two theory papers out on this, one done by our chair was involved in. And this led to a recent speculation by Seamus and I that at high fields you see a small electron pocket in these materials despite the fact that it's a whole dope material. And the classic explanation is you had a biaxial charge density wave state, but we have an alternate scenario based on a biaxial pair density wave state that gives a very different kind of electron pocket, but is still an electron-like pocket that has properties, de Haasson-Alphen frequency and effective mass, that looks a lot like the de Haasson-Alphen data. So this brings me to the question of the origin of superconductivity. Phil's original ideal was that you had a doped mod insulator or a doped spin liquid. People like David Pines earlier pioneered the ideal that you had spin fluctuations, much like what had been proposed for helium-3. And of course, there was an explanation based on Coulomb correlations, which I'm not going to talk about because Dirk's talk after mine will be on this topic. And again, the role of charge fluctuations in lattice and its influence on superconductivity is something that's still under a lot of active debate. One thing I would like to say is the really dramatic improvement in numerical studies that have happened over the last decade. Techniques like density matrix renormalization group, dynamical mean field theory, functional renormalization group, quantum Monte Carlo. These are PEPs and DMET are basically based on quantum information theory. And these states all say pretty much a dramatic, interesting thing, that if you look at the doped Hubbard model, typically you will get modulated spins, modulated charge, and modulated pairing order parameter. So basically you get a PDW state which mostly also has charge and spin modulations present. And all these states are very comparable in free energy. So small changes in the theory can stabilize the superconducting state, it can stabilize a pair density wave state, it can stabilize a CDW state, or it stabilizes an SDW state. And this is what makes this problem very hard, that for strong correlations you have many states with comparable free energies that compete with one another. So imagine you think it's like Phil, that superexchange is actually what's causing the pairing. Is there something else that we can do? And the answer is yes, maybe if we could find cuprate analogs which differ enough from cuprates that could tell us whether we're on the right track or not. So this is you think all the square planar cuprates that you know have been made, and the answer is no. There's this material out here, one report in the literature from the 1970s, hard to grow hydrothermally at high temperatures, but this material actually is interesting in that the copper-oxygen bond angles are about 120 degrees. So if a superexchange interaction was evident, this type of material should have a strongly suppressed superconducting transition relative to square planar cuprates which have 180 degree bond angles. More or less also the coppers are in a near octahedral coordination. So growing this material and then doping it by replacing tellurium by antimony could tell you a lot about what's going on. Of course, a real quantum spin liquid was discovered about 10 years ago by Dan Nocera's group. This is the so-called Herbert Smithite, which was a pretty rock that I showed on the cover of my first transparency. And this material actually has no long-range order, and the coppers sit on a Kagome lattice, which is a frustrated lattice, 120 degree bond angles. And again, people were thinking, wow, if we could dope this, do we get some sort of superconducting phase? And the proposal by Igor Mazin was that you would get an F-wave superconductor, sort of analogous to what Jim Sauls and I have proposed in the past for uranium platinum-3. The problem you run into this case is that people have doped lithium in the material and you basically get nothing. Material remains insulating. And so this is a problem I said before. Cuprates are sort of an island of stability where the dope holes are mobile. Simply replacing oxygen in this case by hydroxides changes the degeneracy between the copper and anions in such a way that you get polaron formation. If you look at the band gap in the material, it's about 3.5 electron volts, so it's more comparable to nickel oxide than it is, say, to a typical cuprate. And we have this new material, so the question is, can you do Kabgome for a copper lattice, a copper oxide lattice? And the answer is yes. We found this material by looking through the mineralogical database. It was found in some volcano in Kamchatka, but because it's an oxide, it can be grown. It was grown by John Mitchell's group. And in fact, if you grow this material and dope it with zinc like Herbert Smithite, you get a quantum spin liquid out of it. But doping studies where you would actually, say, replace like vanadium by titanium, where you could dope carriers into this material, has not been done yet. So some people have speculated maybe we can go other things besides copper. So if you're thinking copper, the next thing down is silver. And it turns out that silver oxide doesn't work for various reasons, but if you had silver fluoride, it would work. It turns out that the relation between silver D and fluorine levels, P levels, are about like in copper D and oxygen P. The problem is getting these materials to form square planar nets is difficult because silver prefers to be D8 and D10 configuration and doesn't like to be in the standard type of Jahn-Teller environment that copper likes to be in. So if you look for the conditions at getting flat sheets, elongated octahedra, fourfold axis oriented along the C-axis, it's tough to get something in here. The proposals do this by MBE. I don't know if Jim Eckstein's in the audience, but Jim probably doesn't want to put fluorine into his MBE machine. But this has been the proposal for maybe realizing this class of materials. And last, there's been a lot of speculation about nickelates. People have tried to make cuprate versions of nickelates, and the most promising thing is to take this 4,310 Ruddleston-Popper phase and do a topotactic reduction to 438. And this gets you nickel in a square planar environment with a valence comparable to overdoped cuprates. So when people did this with the lanthanum variety, it didn't look very promising. You got a charge-ordered insulator, just like you get in doped lanthanum nickelate. But if you go to the praseodymium version, the thing becomes a metal, and the temperature dependence of the resistance looks remarkably similar to overdoped lanthanum cuprate. So it looks like we found the first nickel analog of a cuprate. The problem is, to get in the superconducting region, you have to electron dope the material. And cuprates are easy to hold dope. They're not easy to electron dope, and this has been the problem. So there are various proposals about how one might be able to electron dope this material and get it down in the superconducting region, but so far it hasn't been done. So the last speculation is other class of material. And iridates became a big subject about 10 years ago because it turns out that because of spin-orbit coupling, the T2G bands in this material become a quartet and a doublet, and you have a half-filled doublet in the iridium case. So you have a half-filled band just like you have in cuprates, and the ideal was whether this would be a cuprate analog. The issue in the iridium case is that the iridium P bands, the iridium oxygen P bands and iridium D bands are not close together like they are in the cuprate case. Still, there were a lot of speculations by people like Sentel that they might be superconductors, and although superconductivity hasn't been seen, one does see pseudo gap-like phenomena very similar to cuprates, including Fermi arcs that at low temperatures seem to go into a D-wave node. So although so far this class of materials is not superconducting, it does have pseudo gap-like effects to it. So we're still searching for a cuprate analog. We haven't found one yet, but I think we're probably pretty close to getting one, and we think that if we can find it, it might tell us a lot about what's going on in high-temperature superconductors. So at that point, let me conclude. Thank you very much. Yeah.
About your pockets and quantum oscillations.
Yeah.
So the pure density wave is a more complicated beast than the charge density.
Yeah. Right.
Mixtures
So, because I was like the same boat that Shaquille O'Neal was in, I didn't have a chance to go through this. So what happens, of course, in a CD, if you have a CDW folding of the zone, you know the pockets will support quantum oscillations. If the folding is done by a modulated superconducting phase, it's not clear, because if you look at this so-called electron pocket, this side of the pocket is electron-like, that side is hole-like, and therefore it becomes questionable about whether you actually get quantum oscillations from such an object or not. Our content is, if you look at the thermodynamic free energy, it turns out that only the particle-like content of the state enters the thermodynamic potential, and if you look at the particle-like content, it is non-zero along the whole contour. But there are other proposals that to actually do this contour, you have to have an Andreev reflection at these ends, which might work in momentum space, but in real space leads to a loss of current. So what I will say is that no one has done a full quantum mechanical treatment of this problem. And I have a smart postdoc who claims that they're going to tackle this. Used to work with Alan McDonald, so if somebody's going to do it, he's going to do it, but so far it hasn't been done. So there's a lot of controversy about whether these things will actually lead to quantum oscillations or not. But it certainly has a right behavior. It is an electron pocket, that is, if you increase the chemical potential, the area of the pocket increases. Frequencies are comparable. You have a Lifshitz transition. You have an effect, and that leads to an effective mass divergence, which is also seen in quantum oscillation stories. So the phenomenology looks good, but whether the theory holds up in the end remains to be seen. Yep. Yep. Yeah. 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 Right. Yeah, I do. So first off, I don't know if Tony, you know about this. So they twisted graphene sheets that are about a magic angle of 1 degree to form a moire pattern, and you get an insulating phase and regions of the phase diagram which correspond to like half filling for cuprates, and on either side of the insulating phase you have superconducting domes. The interesting thing is, if you look at the ratio of Tc to the Fermi temperature, and you plot all the materials you know about, the thing that comes closest to is helium-4. So this looks like something that's really in the Bose condensate limit. Tc over Tf ratio is about 10%. The question, though, is because of this, people have speculated that this half-doped state is a Mott state, and therefore when you dope it, what they do by ion gating, or basically by voltage biasing, that maybe you get some sort of unconventional superconducting phase. My feeling, and my colleagues like Alan McDonald, I've been talking about it, I think it's phonons. The reason why you can think about this is if I twist this material, the electronic structure is extremely sensitive to twist angle, and therefore you expect to get a very large electron-phonon coupling, very similar to what you see, say, in magnesium diboride. So my bet is on phonons, but I could be wrong.
So the Tc is very low.
Tc is low. It's about 1.7 Kelvin. But it could be a cuprate analog. I may be wrong.
So do all these classes of materials displace resonance peak in an asymptotic scattering?
Well, so of course the cuprates do. They have this resonance peak. It's been seen in the iron arsenide superconductors. It's been seen in several heavy electron compounds. The classic example of this, explanation of this, is that if you have an order parameter that changes sign under the magnetic wave vector, then you will get a resonance in BCS theory. So that's a classic example. But our chair will tell you that there's an alternate explanation based on stripes that can equally explain the data without having anything to do with superconductivity. So. Okay.
He will talk about Coulomb interactions
that work? Yeah. Okay. Well, first of all, thanks very much for an invitation to such a thrilling and joyful event. The first time that I remember that I met Tony Leggett was in 1993 near Trento. There was a conference on Bose-Einstein condensation. And maybe Tony remembers me a little less than I do remember Tony because of very, let's say, scientifically involved discussions on the part of Tony. Hank Stove and Tony were discussing about, I forgot what it was, but it was quite intense. I remember that. Then the later time we met was in 2006, but I'll come to that. So actually, I added a few more subjects, and that is, I'll talk also about Josephson plasmons in the interlayer tunneling scenario, very briefly, by the way, and about Leggett excitons, but I'm not even sure that Tony actually saw that story ever, so it might be the first time you see that story from my side. And then about the work that we have collaborated on this, Tony, on the high Tc superconductors and the Coulomb interaction. So let's begin with interlayer Josephson plasmons. Cuprates can be thought of, if this is the c-axis, as stacks of superconducting layers. These are copper oxide and oxygen planes separated by insulating barriers. And since it's like this, but indeed the material is like this, you can think of it as layered superconductors where you actually have the Josephson coupling between those planes. So if you have Josephson coupling and you have these planes which form sort of a capacitive stack of many capacitive plates on top of each other, then actually between each of those planes you can think of this connection as containing a capacitive link, which are the plates itself, but also a Josephson coupling, which is the tunneling between one and the next layer. So there's a sort of a inductance given by the Josephson coupling energy times universal constant, and these capacitance which are just given by essentially by the geometry of your material. Then, of course, you can also think of it, each layer being sort of a bucket filled with the electron, actually these Cooper pairs, and they can flow from one to the next bucket. If you now set up a plasma resonance from here to there, actually the total charge in each of the buckets remains the same, except for the extremal one. So the total charge oscillates between this and that one, actually flows through the other ones. And that sets up a ordinary, more or less ordinary plasmon, but made out of Cooper pairs. And the resonance frequency of that is given by the square root of the inductance divided by the capacitance. If you do an optical experiment, you measure the real and the imaginary part of the dielectric constant, epsilon 1 and epsilon 2. If you take omega times epsilon 2, you get something that we also sometimes call the optical conductivity. And there, in this case, you would have, along the c direction, so between the planes, just a peak, a small peak, because of the superflow from one layer to the next. But since this flow is I mean, of course, the connection is only very weak. As Josephson coupling, there's not much spectral weight in this peak. And then at some low frequency below the gap, we have a crossing of through zero of the dielectric constant. That gives rise to a plasmon. If you then calculate the imaginary part of minus 1 over epsilon, this is known as the loss function, this gives you a peak right where you have a zero crossing here. So the zero crossing corresponds to a pole there. So this is the sketch, and this is what it looks like in experiment. Do you have a better pointer, maybe? I'll keep talking with this pointer, it doesn't matter. So what's plotted here is one of these cuprates, it doesn't matter which one, it's lanthanum, strontium, copper oxide, where what you do not see here is this delta function, because you do not measure zero frequency, you only get finite frequency. Thanks. Okay, now this is I got another one now. Yeah. Okay, but this is fine. I can work with these two things. So what you have here is the opening of a gap in the optical conductivity. There is a phonon which is not important. That's why I made it somewhat grayish. And here you have this zero crossing of the dielectric function. Where it crosses zero, you get a peak in the loss function. This is your plasmon, and there's a delta function in the optical conductivity there. Those are the two poles you have. Actually, that kind of observations was related to the rise and fall of an interlayer tunneling scenario of Phil Anderson. So the stage was set by a paper by Chakravarti, by Anderson and Strong in 1993. Then there was a further paper on that in 1995 by Phil Anderson, where they said the source of superconductivity is actually coming from the fact that you allow pairs to tunnel from one plane to the other. So it actually starts from the principle that for some reasons that I won't talk about, the ordinary tunneling process is blocked, but then as soon as you form pairs, it releases that kinetic energy blocking, and this by itself is then a reason why the Tc should be equal actually to the plasma frequency square that I just spoke about times known factors, just symmetrical factors and so on. Okay, that was the stage. Then came the nailing down by experiment whether or not there is such a correlation. And it actually started, and this was 1996, where Tony and I were at a meeting which celebrated the 10th anniversary of high Tc superconductivity. I gave a talk which probably nobody in the audience understood except one, and that was Tony, because I spoke about this kind of tests, and we had already done some preliminary tests, and Tony was at the same time already working out the theoretical constraints on that kind of tests. So he published this paper in Science. We kept working on that. We only had of course, the paper wasn't ready yet, and only in 1998 we were ready with the experiments using optics, and there was an additional set of experiments using scanning squids by Catherine Moller in Princeton, and so that led to this publication, which actually showed the following thing, namely the omega j square in thallium-2, barium-2, copper-06 was only 400 times smaller of what it actually should be to explain Tc. So the mechanism of Anderson was a factor of 400 too small in this case. And so this gave the situation after the fall of 1998 where the motor MS ILT went down and the crew tried to escape. I also showed this graph in Princeton shortly after, and Phil took it very, very well. Yeah. So now we get to multilayer couplet plates, and that's actually where another story comes in. So in 1966, Portonier predicted for superconductors with two bands of charge carriers a collective oscillation corresponding to small fluctuations of the relative phases of the two condensates that form inside the two bands. And that corresponds to a kind of excitons inside the superconducting gap. This is the paper. It's a long paper, but the message itself is quite simple, actually. In principle, those excitations should be observable with electromagnetic radiation, either Raman spectroscopy or infrared, depending on details of the material. But in practice, that effect on the infrared optical properties of most superconducting materials has been too small, probably too observable. But there's an exception. There are two, actually, but I'll talk about one of those. So if you now make these same kind of superconducting stacks as before, but you make an alternation of one kind of junction with samarium oxide and another kind of junction with lanthanum oxide, you alternate in this way, then actually, even though the superconducting layers themselves are still equivalent, they're just mirror, they have just lanthanum oxide left and samarium oxide right, or vice versa, otherwise it's equivalent. But still you have now a larger unit cell which contains now indeed two reservoirs of superconducting fluid. At the time we were thinking about in 1996, this is one of the most cited papers in the Czech Journal of Physics. You know, 100 or 150 citations. It was a failed PRL, I should say, that we put in as a conference proceeding. This is the equivalent electrical engineering diagram that you get. So you have an L1 and an LC corresponding to this link, and an L2 and an LC to corresponding to this. So just alternating with still the same buckets everywhere, but different kind of pipes connecting them. I have left out one important ingredient here. I'll come to that. And so we could actually do this engineering calculation, and it gives an equation for the dielectric constant, also for the real and for the imaginary part. If you plot it, there is not one, so rather than having only a delta function at zero frequency in the epsilon 2 in the imaginary, in the dissipative part, there's an additional peak. It's also called transverse optical plasmon, that's what we called it. And there are two zero crossings of epsilon corresponding to two plasma resonances which are longitudinal. All of these excitations are along the c-axis. It's just how they are oriented with respect to the propagation direction, which we take actually to be in the infinite wavelengths limit here. So at the same time, several groups started thinking about it. Here are three papers in PRL in the same journal. In fact, this was, let's say, also by intervention of the editors of PRL, that they actually put 3 experimental papers independently confirming this picture, of which I show one, which was from our own group, showing that indeed there is this peak over here in the superconducting state. The red curve is in the normal state. There's a peak over here. There's a zero crossing here. And this would be a zero crossing were it not that there is a sort of a damping, so it's only a small wiggle. If you calculate the loss function, it gives 2 peaks. However, in all 3 papers, it was noticed that this peak here was 20 times smaller than that peak. Note, this is actually a log scale. Just to make it visible, you have to plot it as a log scale, and this is way too small, a factor of 20, and that was actually seen in both cases. So actually the agreement wasn't so good, it's just that we saw the 2 modes. Okay, the remedy was actually the solution of that intensity conundrum was that you have to take into account the incompressibility or the finite compressibility of the superconducting reservoirs, so precisely what Leggett had done. This was actually pointed out to me by Bolejewski when he was visiting in Groningen at that time. And so, actually, we did it. We actually derived a different, well, the same expression, but we have a different meaning of the microscope of the parameters. Actually, you can show that if you put in a density of states of 0.8 electron volt minus 1, corresponding to a compressibility factor, related to this density and lattice parameter, then this is you actually get precisely this factor of 20 over here. So, indeed. This is the element that was missing, and that was Leggett's story. So in a way, you may say, yes, we have Leggett excitons here in a particular kind of environment of Josephson-coupled multi-layers in the cuprates. Did you know that story, Tony? No, that's good I told her. Okay. Let's come now to the title of this talk, Coulomb interaction in the mid-infrared scenario in high Tc cuprates. This is work that we also started somewhere around 2001 probably, or 2000, 2001 I think, when Tony was visiting in Groningen. This photo is a much later date, by the way. This was in 2015 at the M2S conference where we were discussing together the results and the interpretations of them. Involved in this work are people from my group, 2 postdocs, a senior associate, and a master student. Christian was a PhD student at the time in Groningen, but that's 15 years ago. And Genda Gu from Brookhaven, who provided samples. And then, Dominique Pouliot is over here, partly. Laura Green, Jim Eckstein, and Tony Leggett from Urbana-Champaign for discussions and theoretical support. We had very intensive discussions, in particular with Tony at a certain point. Now, first, a few words about high Tc superconductors. We heard about this phase diagram. I just took the latest one that I stole from the review of Keimer, Kilverson, Mike Norman, Uchida, and Zanen. There's more complexity in it than I will talk about. But the important part here is you have superconductivity in the green part. This is hole doping, and this is temperature. Here you have a superconducting gap that's expected. Here we have a sample where in 1998 the Renner and Fisher measured the tunneling spectra, which is actually density of states as a function of energy. And what you see is below Tc, there's a nice gap. Not a full gap, it's a D-wave gap. That's why it's not completely going to zero, a nice gap. You warm up, you reach Tc, that's where the white line is, and there's still a gap. You don't have these quasi-particle peaks anymore, but there's still a gap. And you go up to very high temperatures, even at 290 Kelvin in this particular case of an underdoped, there's still a little bit of a suppression around EF. So there's always a bit of a gap. And so you're actually coming down around here-ish, and you still see a gap, a very gradual opening of a pseudo gap over here. It's a very clear feature seen in many, actually in all spectroscopic probes, including optics and ARPIS and Newtons even. If you go overdoped, they don't show the graph, actually the gap only opens in the superconducting state. And even for the optimally doped, it's more or less a superconducting state. So here you have this strange metal phase. And there you have a pseudo gap. Now, where is the T star? I mean, where actually does that happen, this opening? This is something that John Loram, who very sadly passed away half a year ago, made studies of. And he calculated from his specific heat data shown over here, the entropy as a function of temperature. This is for different dopings. This is underdoped, this is overdoped, and optimally doped. Now, entropy in a metal should just be a linear function of temperature and extrapolate to 0, which is the case for the overdoped side over here. But here, that is not the case. It doesn't extrapolate, it's actually undershooting. Now, what you would expect if the pseudo gap would close is that those curves would come back to some straight line that does extrapolate to 0, but it actually never happens. And that's a very strange thing. You don't actually see in these thermodynamic measurements an indication of a pseudo gap closing temperature. Here is an optimally doped sample from LORM, and what is shown is the specific heat itself. Again, calculated is the entropy from it. And you can also calculate, sorry, not the entropy, this is the internal energy now, the integrated specific heat. And what's shown, the dotted line here, is the extrapolation of the normal state by satisfying certain entropy balance constraints. If you follow that extrapolation and you look at the difference between what it is here and what it would be if the system would not go superconducting, this difference is called condensation energy. In this particular example, it's 1.57 Kelvin per copper atom. Now, what Leggett pointed out in 1999 is there's a very interesting way to look at the mechanism of superconductivity in a very agnostic way, without really talking about mechanisms in the sense, this mechanism, if you talk about mechanism, you think of, let's say, an old Chevrolet with a motor in it or so, this kind of mechanism, or something in a watch. And so this is sort of, these mechanisms are not always very reliable, as we know also from the Chevrolet example. And it's also true for European cars, by the way. So to do more reliable things, but say less specific things, you can also think about general approaches. And this is what Leggett actually, he dug up an argument by Chester, 1956, where he said, okay, if the Hamiltonian has two terms, kinetic and Coulomb, and this is the total Hamiltonian containing everything, electrons and nuclei, then you can distinguish two terms, the Coulomb interaction energy, which is just the average of this part of the Hamiltonian, and the kinetic part. And the virial theorem will tell you that this part here has to be precisely minus half that part. Okay, so far so good. So if you take the average of the total Hamiltonian, this is going to be precisely half the Coulomb energy. Good. Now thermodynamics tells us, that's what we previously saw, this energy average, the internal energy that we saw from the specific heat experiments in the superconducting phase is smaller than that in the normal phase. And the difference is precisely this condensation energy. Now if that is true, then it implies that also the Coulomb energy, which is just half this, should also be smaller than in the normal phase. In other words, the Coulomb correlation energy of your total system has to be smaller in the superconducting state than in the normal state, otherwise it would not be thermodynamically stable. Now the nice thing is that the Coulomb interaction energy can be measured. And that's actually because there's a nice relation between the charge-charge response function and the loss function, which is related to the loss function that I spoke about. It's just the charge-charge response times the Coulomb potential in momentum space. That gives you the loss function. And actually this fluctuation dissipation theorem relates this to the total Coulomb energy. It tells you that if you take this loss function, you integrate over all frequencies, multiply with a Bose factor correction, and you sum over all momentum, it gives you the total Coulomb interaction energy. This is it's an oxymoron. So actually this is, it's completely true. There's no way around it. This is just, it's not an oxymoron. It's a very subtle and nice result from the fluctuation dissipation theorem. So this can be measured at Q non-equals 0 using electron energy loss spectroscopy that I will not talk about, but I will refer about it at the end. Or for Q equals or very close to 0 using optics, namely spectroscopic ellipsometry. And so how do you do ellipsometry? You measure the reflectance of a ray of light on a surface using two kinds of polarization, S and P. You take the ratio of the two coefficients, gives you Rp over Rs or Rs over P. You put it in this formula and it gives you the loss function. There's a whole lot more to it having to do with correction for the c-axis and all that, but this is the basis of it. And if you do that, this is the loss function after correction for the c-axis. This is what you get if you do energy loss spectroscopy in transmission. And this is for cuticle, well, very small. That's quite similar to what we find in the optics. Of course, here you can measure also dispersion, as we cannot do in optics. But in optics, we can measure things very precisely as a function of temperature, as in this example. Here you're looking at 300 spectra for 300 different temperatures. Sorry, it's 280. So we start at 10 Kelvin approximately. You go to 290 Kelvin or 300 Kelvin, I forgot. And every Kelvin there's a spectrum. This is such a loss function, yes, from 0 to 3 electron volt. It has a peak at the plasma frequency. This is now the loss function in the plane direction, I should say. That's why it's not the Josephson frequency of 10 milli-electron volt, but this is actually 1 electron volt of the planar response. And so here you see how it depends on temperature. So not very much, you would say, if you blow it. Oops, what did I do? Oh, okay. If you just blow it up a little bit on the top, you see it better. That is actually a little extra nudge over there. So you see that the entire peak is actually getting a bit more intense going into the superconducting phase, because this is where Tc is for this sample. So that would actually correspond to an increase of Coulomb energy, by the way, in this case, just using that formula. So now Leggett actually made further statements. He said, okay, where would the main saving come from? He used what he called the Willie-Sutton principle. There's no time to tell you that joke, but it is a nice joke. But probably many of you heard it already. So the main energy saving has to come from the loss function peak around 1 electron volt, and also where the peak is strongest, and we saw it is strongest for small momentum. The reason is that there is most of the spectral weight anyways, and so if anything changes, this would have the biggest influence. There's a much more subtle and microscopic reasoning behind it, which essentially means that the main saving of Coulomb energy is caused by the system changing its screening, where you go from normal to superconducting, and that's profiting mostly from that part of which we saw the spectra just now. Okay, so here are two examples now. This is a so-called underdoped sample on this side. If you follow the total Coulomb energy, that's this integral here, that's just, or actually the integral around the peak over here, it becomes a little bigger when you go superconducting. You can also see that there's much less intensity coming from those two wings, so the main part comes really from here. And if you go overdoped, you should look at the black line. The red line is an extrapolation. It has the opposite sign. So here the Coulomb energy gets smaller in the superconducting phase. Now, as you can, there's only two examples. I'll show here through the entire phase diagram, where we go from here, which is 99.5% doping, to about 23% doping. So from here to there, you go from there to there. It's all showing that if you go in the superconducting phase, on this side of the phase diagram, this spectral weight increases, and so that means there's an increase of Coulomb energy. That's opposite to the Leggett scenarios that I spoke about. If you go to somewhat overdoped, there's no effect, and you go further overdoped, and the kink goes the other way around. So here you have Coulomb energy saving. You can also look at the derivatives, and using those derivatives, you can actually, using a small trick, make a reproducible estimate for all the different samples about this condensation energy with a weak assumption about what the temperature dependence is below of the normal phase. So that's what I did. Then you have to say, okay, what does it mean now for the total Coulomb? Here we look only at one Q value, but you should, of course, integrate over all Q values. There we have to go really into the details of Leggett's idea. He said, well, in principle, this Coulomb energy change that you measure at Q equals 0 is more or less what you would have for all values of Q parallel to the planes up to a certain limit, which is 2 divided by the, divided by the distance between the planes. And so you just have to integrate over that number, and you would get the right value. There are different ways of doing that, but time is running fast, and I should go. Actually, we tested different ways of doing that extrapolation, making different kinds of assumptions about whether you have a single layer only, or you have a stack of layers, or you have a stack of bilayers, and so on and so forth. And all these different extrapolation schemes give the same prediction, essentially. These are the different colors. So this is what you would get if you assume that all Q values in the Brillouin zone have exactly the same value as what we measured This is what you get if you assume you have this inverted hat shape. So you get about 1/3 or so of the maximum estimate. And so if doing that for all these different dopings, this is what the Coulomb energy looks like. It's increasing for the lowest doping, and it is decreasing below Tc for the overdoped samples, and there's a point where it doesn't change. And these are the corresponding condensation energies from John Loram's work. And so there are different things you can conclude from here. Let's say the Coulomb energy changes we see at least are in the right ballpark, but they do not always have the desired sign. So there's not a simple message from here, which is good because the purpose of this talk is to give you an idea of what future research might look like. Well, this clearly is not a completely closed issue. So we have been floating around various kinds of ideas why this is increasing over here. One possibility would be that on the underdoped side, you already have pairs in the normal state. And it's those pairs that condense. And then there is no simple way to predict what this Coulomb energy would do. So this could be different from what you see on the overdoped side. Then, of course, you could argue that, okay, we only looked at Q equals 0. You really would have to look at much higher momentum values, maybe at the zone boundary or maybe even beyond. And for that, one needs to work with different kind of techniques than we actually have applied. But there's also a lot of hope in here. We are not looking at numbers here, which are ridiculously different from what you find from this condensation energy. It's not a factor of 400 smaller, nor is it a factor of 400 bigger. So we are in the right ballpark. Given the somewhat crude assumption that we made about how it actually depends on k-space, you could easily imagine this to be a factor of 2 larger, but also smaller, even within in that model. And it is easy to imagine that with this kind of numbers, by actually collecting all momentum information, you would actually find something that agrees with the experiment. Of course, it's also true with this model that it cannot be wrong. If you take all momentum values and all energy values, in the end, you should actually get precisely the same result as for the condensation energy. Okay, that brings me to the conclusions and the outlook. So the multi-layer couplets, there you have Josephson plasmons and Leggett excitons. If you do the test of the mid-infrared scenario, then we find the correct size more or less, but the sign is not always correct. And there are a couple of open questions. For the underdoped samples, are pairs already formed above Tc? And where is the T star if there is a T star at all? It could also be a crossover, as Mike said. For the next decade or so, well, we need EELS probes of the same quantity, so we actually have to measure really the correlation function and in momentum space, from which we calculate also what the direct space correlation function look like. And we have to do that in very small and precise temperature intervals. That's the end of my talk. I've profited enormously from discussions with Tony over a very long time, and I really thank you for that. And I hope, Tony, that we can continue in the future. I'm sure we will. Thank you for your attention. Sure. I didn't put it in now just because of time, essentially. Of course, we have done work earlier on, much earlier on the kinetic energy. This is the kinetic energy in the sense of the band energy. So it doesn't really fit precisely in this diagram that I just showed. Sometimes I do fit it in the same diagram, but always keeping in mind that when we talk about Coulomb energy, we really mean the true Coulomb energy. And when we talk about the kinetic energy, it does not correspond to the kinetic energy term of that same Hamiltonian. But grosso modo, it behaves the same as the Coulomb energy, but with the opposite sign. If you put it in the same diagram, you find it the same point where it crosses 0. You get it from a different sum rule, which concentrates on the optical conductivity at low frequencies. But there is, you can always pose the question, are we looking at really independent quantities or quantities that are still related through Kramers-Kronig relations? I guess we are. Although in principle, you could imagine that the two measurements that we do, ellipsometry with this sum rule, optical conductivity with a different sum rule, really give different types of information about the material. But yeah, they do cross 0 at the same point in as a function of doping. Yeah.
How close is the correspondence
Well, the anomaly, so you have to make a precise definition of where you say in such a graph what the anomaly is. So that's precise within 5 degrees just from the experiment that we do, or maybe just from the resolution that we get from the spectra. This is already clear if you look at, well, even if you look at a graph like, oh, it's not here now anymore. I have one of the best ones here. It's actually one of the recent ones we used a few months ago by BCO. Even there, you see a very nice kink, but I would say this is not more precise than 2 or 3 degrees. So it's that precise.
But if you go through T star, in one of the underdoped ones, there's nothing, right?
There is nothing. I can give you tens of examples of attempts where we, of course, when we discussed it, in the time when we started to discuss it, all samples, all data, there were all kinds of kinks and bumps on the road. And it looked very promising, and Tony and also and collaborators got really very excited about it when we repeated the experiments and removed the bumps from the road by just doing the experiment better, with better vacuum, for example. Then those disappeared. So actually, these are very smooth curves. If you look at derivatives, you just see noise, but nothing that you can put your finger on. This is T star.
So that's bad for interpretations of T star in terms of free-form carriers.
I wouldn't necessarily say so. I think this is very nicely consistent with a fluctuation kind of peak. This is actually a paper I didn't talk about, but that we wrote with Tony not so long after this interlayer tunneling business, where you actually see for the somewhat optimally doped and weakly underdoped samples, you see a fluctuation peak around Tc that spreads out over 50 or 60 Kelvin. There also, it seems that this peak just approaches asymptotically 0. It never really makes a kink. Now, there's no, okay, I mean, different experiments can give different things there, but it depends also on the compound, I should say.
So what about the
Tony had also a
C-axis?
question, you don't see me.
And what about the C-axis response? Because this is Q equals 0, but there's still, I mean, it has spectral.
Yeah. Okay, read our long PRX. It is in appendix F and G, I think. If you go through all the moves, you calculate how much it could contribute, it's negligible. And that's because the plasma frequency along the C direction is so small.
No, I mean, is there some behavior?
Well, yeah, there is some behavior in the sense that there is no plasmon in the normal state, and it is there in the superconducting state. So if you take that and you do the integral, you will probably find that the Coulomb energy increases going superconducting. But that's a very, very tiny amount. It's a factor of 100 smaller or so than what we actually see along the AB plane.
So you mentioned in your extract that only a rather small fraction of the total Coulomb energy comes from energies below 3 eV, and that one should really try to probe to much higher energies. Do you see that as a practical possibility in the next decade or so?
Okay, so it wasn't audible for the audience. Tony asked about a point I put in the abstract, didn't mention now, that we know actually from analyzing the experimental data and discussing also in terms of Tony's model, that what we actually see is sort of the tip of the iceberg. We can actually infer from our data that there should be 4 times more or 5 times more change of Coulomb energy in a range somewhere between 3 and 20 electron volt, to which we didn't have access optically, at least not with this spectrometer. So the question is, can this be observed in the coming decade? Yes, I think so. In fact, it is not so difficult to extend the range to higher energies. 6 or 7 or 8 eV should be no problem. Going to 20 requires soft X-ray. In a synchrotron can also be done. Just a matter of manpower and getting your very stable and well-aligned and stably aligned cryostat inside this beam line. Yeah.
I should add in that context, like there was some work done at Urbana on this by Miles, where they saw evidence of changes around 5 volts in non-operator.
Yeah.
Okay, let me start by thanking the organizers, Dale and the other organizers, for this honor of speaking at Tony's birthday. It's a great pleasure, and I also want to add the voice of my colleagues from Ohio State, Mohit Randeria and Jason Ho, in saying happy birthday to Tony here. So I chose this title, Broken Paradigms, because as I closed my eyes and thought about Tony, I first met him in 1987 when Mohit and I came to Urbana as postdocs. Mohit was in Tony's group, and I was working with David Sepperly, and he took me in spite of my having no numerical skills. And that takes real courage. But I'm delighted he gave me that opportunity, and Mohit and I were able to bring our skills later together, you'll see, in working on some of the problems of superconductivity in various forms. So the reason I picked this topic, broken paradigms, is because in a way it crystallizes for me what Tony has done in his own research. It's also the first time I ever saw anyone talk about, Tony once gave a lecture on the structure of scientific revolutions or some such philosophical topic, and he did that sitting down and reading from several sheets of paper. And I kept waiting for the PowerPoint or some slides, those were the days of slides, to come on and see some structure in a bulleted form, because that's all my brain could take in were bullets of information. And here was this philosophical talk that sort of went through these logical developments. But that's really Tony in terms of bringing his knowledge from different directions. I also want to thank Haruko and Tony for their tremendous hospitality. Every occasion we were invited to their place for these fantastic dinners with utter chaos, but Tony was always there giving us our drinks and food, and they've kept us in touch with us year after year through their annual letters, something I've never managed to do. I'm only able to, at most, make a small card, but it's amazing. They're able to put together this. Maybe it's probably Haruko that does it. I'm not sure. I have to ask her. And you've already heard about this picture. It's been talked about. I picked it quite independently because in 2003, I think we were back in Urbana on sabbatical, and my children also got to meet Tony at that time. And when I told them that Tony Leggett has a Nobel Prize, this doesn't move. Okay. When I said, Tony has a Nobel Prize, they were like, what? Our Tony? And that, in a way, summarizes how they felt about him, because he was so approachable that, they were never like on a pedestal. And in a way, no, that's fine. I'll just use that. In a way that really makes him so accessible to little children. So this is, I think, a very real picture of how he interacts with everyone. Now, what I took away from Tony was precisely these two things, and much more, but these two things in my mind really captured some of the essence of what I learned from him. And one was how to ask good questions. And I put good in within quotes just because, that can mean different things to different people. But really, there is a way you can ask a good question, and then how to make them sharper. So I'll try to show some of this evolution in my own research. So to begin, since this is on broken paradigms, I want to say, let me bring this all up here. I want to say that our field has really gone through major revolutions, just in terms of when I came in as a graduate student and the paradigms we were learning at that time and how they have been broken over time. And one of the big themes is fractionalization. So you can see an electron or even a quasi-particle in Fermi liquid theory getting fractionalized, for example, in the quantum Hall effect, or the charge and spin getting separated in Luttinger liquids, or you might have magnons, which are basic excitations of a ferromagnet or an antiferromagnet getting fractionalized into spin-half spin-ons. And these are not just figments of someone's imagination. Theorists have been proposing these, but the real, it's been just amazing to see how experiments have verified this through seeing the, for example, a specific heat that is, seeing linear specific heat and thermal conductivity that is proportional to temperature, very much behavior, which is what Fermi liquids or something with a Fermi surface would give, but in an insulator, which has no Fermi surface, but it's these emergent spin-half spin-ons, which are fermions, making such a Fermi surface. And these have been observed. And, seeing monopoles in quantum spin liquids and so on. But what I want to do today is tell a more personal story. And as I was trying to construct this talk, I was seeing that there are so many threads to these stories. And I promised to tell you just one story so it doesn't get too chaotic. And even in that, it's a bit like this Harun and the Sea of stories, one mingling with the other and so on. And even these are not sort of straight trajectories, because very often you see the same, you come back to certain ideas many, many years later. But anyway, let me get started. So I'm going to first I'm going to start with the superconductor to insulator transition driven by disorder. So we start with these two big paradigms. Anderson localization, which essentially describes disordered systems in the absence of any interactions. And we know by now how these behave. You get a mobility edge that separates metallic states from localized states, but there is no gap in the spectrum. So these are gapless insulators. You also have BCS S-wave superconductivity, where you have essentially the gap in the single particle spectrum, which controls the transition temperature. When you bring these together, rather surprisingly, I will show you both of these paradigms break down. Now, the reason I got into this, we heard some discussion earlier about the high Tc superconductors and whether they were S-wave or D-wave, and these discussions were going on around 1993, 94. I was at that time in Argonne, and I remember this conference that Tony was there as well. Phil Anderson was also there, and I think Mike might remember. It was extremely spirited and very polarized. You either believed it was S-wave or D-wave, and people were not listening to each other. And one of the things that struck me at that point was the effect of disorder. So if you have a D-wave superconductor, they were supposed to be extremely sensitive to disorder based on Abrikosov-Gorkov and their calculations. And it's clear why that is the case, because you have these lobes with different phases, positive and negative phases in the D-wave superconductor, and disorder would typically scatter you from the positive lobe to the negative lobe, washing out superconductivity. And yet, undergraduates were working in labs, mixing and baking and shaking and making these cuprate superconductors. So clearly, they were not sensitive to that disorder. So the question was why? And I was kind of coming out at that point more toward the S-wave direction, just because of this, their ability to sustain so much disorder. So when I took on my first graduate student, the problem I gave him, Amit Ghoshal, was I told him, we really want to study D-wave superconductors with disorder, but before we get started, let's just take a look at the S-wave problem, and everything is known about it. We have Anderson's theorem. We don't expect to find any surprises there. So let's just check off that everything works. Then we'll put in the D-wave aspect of the order parameter and go from there. But surprisingly, this beginning took us many years, and we found many surprises. And I have kind of summarized it here in this sketch, but all of this is backed up with several calculations. So what this shows here is an energy scale as a function of temperature, and what you see is the standard BCS paradigm where the gap and the superfluid density measured in some mutual inductance experiment both vanish at Tc. So this would be the standard BCS paradigm. But when you add disorder, what you see is that the single particle gap remains finite for arbitrarily large disorder. You might have expected to find the Anderson localized paradigm at large disorder, but that's a singular point. So the presence of any attraction opens a gap, and that remains finite. The superfluid density still vanishes at some critical disorder and crosses the scale, the gap scale. Usually it's a very large energy scale on the order of EF, but it crosses that and vanishes at some critical disorder. And in this region here now, you would basically open up a pseudo gap. So in other words, if you were looking at the behavior in temperature, then you would see that Tc is given by the minimum of the gap and the superfluid density. And when at low disorder, clearly the gap is the lower energy scale, so that's essentially fitting the BCS expectations. But closer to the critical point, where the gap becomes the higher energy scale and rho s is dropping, now Tc is governed by the superfluid density. Now you might ask, what happens beyond the critical point? Is there an energy scale that goes soft at that critical point? It's clearly not the single particle gap, which is continuing to remain finite. You have to go to the two-particle tunneling, or Josephson spectroscopy, where you try to inject a pair. And when you inject a pair in the superconductor, here, you can inject a pair at zero energy. That's the Josephson effect. This is numerical results. It looks like an experiment, but these are numerical results, and this width is coming from some analytic continuation that we have to do on the Monte Carlo. And when you enter the insulating phase over here, then this peak at zero energy becomes it costs some energy now to insert a pair, and that opens up a gap here in the pair tunneling spectrum. So that's the omega pair, which you can see vanishes at the critical point and then grows as you enter the insulator. So this, in a way, captures the phase diagram when you take an S-wave superconductor and add disorder to that. So the reason behind this is that when you take disorder and in a superconductor, then you get this emergent granularity. Even though the disorder is homogeneous, it creates these puddles on the scale of the coherence length, and these patches are coherent within this patch, but the between patches, they may or may not be coherent. So when you have a superconducting state, the phases on the different grains are locked by the Josephson effect, by the tunneling of Cooper pairs between these grains. On the other hand, when you enter the insulating phase, in that region, due to quantum fluctuations, the phases become incoherent. Now, here we actually connected with some of Tony's work. You see the superfluid stiffness becoming extremely small, and this is even within mean field theory. You can see it becomes very small, and that connects with some of Tony's work where he derived bounds on the superfluid density in a system that has some inhomogeneity. And here we extended that to these disordered systems where you can show that when you try to put a twist on the system, the energy cost of that twist can actually be absorbed in these non-superconducting regions, thereby giving you a very small increase in the energy for a given twist, and hence a very small superfluid density. Okay, so let me kind of march on because I'm losing some time here. So let me just, we've heard a lot about pseudo gaps. When you, in this direction, the phase diagram I showed you was at 0 temperature, and in that case, you saw that the gap in the spectrum was a hard gap. So there were no states within the gap in the superconductor, even due to rare regions coming from disorder and so on. If you take a particular disordered system and go up in temperature, then one could see that you get this pseudo gap where at Tc, the superfluid density went to 0, but the gap closed only at a much higher temperature that you can call T star. That's shown here in the single particle density of states. This is not experimental data, it's actually theory, showing the single particle density of states with a hard gap at low temperatures. The white dotted line is Tc, where the superfluid density vanishes, and you can see this gap still persisting. This was verified in experiments done using scanning tunneling spectroscopy, which again showed the sharp coherence peaks at low temperature. A dotted line is Tc, and you can see even above Tc a huge suppression of the gap that persists almost up to 20 times Tc. So that's a pseudo gap opening in this case due to disorder effects. This is not to say that this is the explanation of the pseudo gap in the cuprates. It's just that different systems can have different reasons for opening up such a pseudo gap. But nevertheless, we are seeing the breakdown of the BCS paradigm, within which at Tc you would have recovered the normal state. And in this case, because essentially, there were Mohit and his collaborators following up on several of Tony's works on the BCS-BEC crossover had shown that as you go toward the BEC regime, you have pairs still existing in the normal state. There it was happening because of strong interactions that were shrinking the size of the pair. Here it's disorder that is shrinking the size of the pair because of localization effects. And as a result, you still have existing pairs in the normal state. Okay. Let me kind of march on. From here, connecting a little bit to what Dirk was talking about, the optical conductivity, you see this is at 0 frequency. This is the superfluid density or superfluid stiffness. As a function of frequency, there's a gap which is 2 times delta, and then you can start breaking pairs and absorbing. But there is this window here where in a clean superconductor there's no absorption. Now, as I showed you, because of disorder, superfluid density is vanishing ultimately at some critical disorder. So you might ask, if superfluid density is vanishing, where is that extra weight going? And it must go into this gap region. And we did quite a bit of work on this in terms of understanding the role of the Higgs modes and the Goldstone modes, but I won't go there right now. So, coming back to my original question, whatever happened to the D wave and disorder? A very short digression here just to say that there was some very beautiful data from Seamus Davis's group that showed that when they made these samples with different dopings and looked at different regions, the behavior at high energies, so this is DI/dV, the density of states versus the bias. At high energies, there were big differences depending on whether you were in a red region or a black region and so on. What changed, these should have been 0.19 and some other doping. This is some typo here. But in any case, it's not important. It just says when you went to different dopings, the fraction of red and black regions changed, but the spectra in these regions were very similar. And what you want to take away from this is that the low energy V-shaped density of states remained unaffected by the disorder. So exactly why that is happening was what motivated me to go into this field to understand why D-wave was so robust. And we have some explanation of that in which we were able to show that if you just put in D-wave weak coupling superconductivity with disorder, indeed then the low energy behavior is greatly affected. These are different amounts of doping, or disorder I should say. The low energy behavior is greatly affected. But if you put in the additional feature which cuprates have, ultimately they are D-wave-like because there are strong interactions. And when you put in the additional feature of the strong U, then the low energy density of states is indeed very robust against almost 25% disorder. And this comes down again to the fact that the scattering is mostly within one of the lobes of the D-wave order parameter and not between the things. Now coming to where are some of the more open questions, the behavior in a magnetic field has been explored quite a lot in transport, and there are many confusing papers out there. But I think the situation is going to get clarified in the next some years as groups are bringing together not just transport, but STM and other techniques. So simultaneously doing STM, superfluid density, and transport on these systems will reveal the behavior much better. And just to give you some of our predictions here, this is the field versus temperature. We have seen that we know this, that you get a Abrikosov lattice at low fields. As the field is increased, these cores overlap and ultimately you get a normal state. But really, how does this behavior change as you go to extremely high fields? It's not clear that HC2, just the usual BCS behavior of HC2 describes such systems, and there is growing evidence that there is the curve really goes up, and it's not even clear it's closing at any particular field as the temperature is lowered. The nature of the vortex is also quite mysterious. One would have expected that when you suppress superconductivity, you reveal the normal state, which is usually metallic. Instead, one is seeing insulating cores in some recent experiments. Okay, so here is another prediction we are making, that just as we saw the gap persisting with disorder, now with magnetic field, also the gap persists, the superfluid density comes down, and there is this region where you get a pseudo gap now opening due to magnetic field, and we expect the vortex cores to have different behavior in these two regions. There's this, typically the experiments in this field have been difficult to interpret because you want to separate disorder and magnetic field. And typically films have so much disorder that when you apply a magnetic field, it's difficult to separate these two aspects. But these experiments from the group at Tata Institute have taken very clean niobium nitride. When there's zero field, you can see this is clearly a BCS superconductor with the resistance vanishing at the same temperature as the gap vanishing. And so it's a good BCS superconductor, but when they apply a magnetic field, that same material shows these density of states, which is a suppression at the vortex core, rather than another system like niobium diselenide, which has a metallic core. So these experiments are just beginning, and I think we'll see much more on that. So moving on to asking good questions. We decided to step back from the complications of disorder and try to ask an even sharper question. And what we wanted to ask was, we know that in the usual BCS superconductor, just a tiny region of energy of order delta, which is much, much less than EF, is perturbed to open a gap. The way the BCS paradigm can break down is two ways. One is the coupling to the glue, whatever that might be, greatly perturbs the Fermi surface, in which case Tc is not given by delta anymore, or you might have a situation where the electrons become slower than whatever mode is trying to couple them. And so that takes you into a non-adiabatic limit. And so you can see that can happen in very low density systems, of which several are now becoming possible. The latest example in that is bismuth, which has essentially one carrier for every 10 to the 5 atoms. So it's a very low carrier system, so EF is really dropping down. And it's possible, so in bismuth it's almost coming close, and other low density systems could actually cross this. But we decided to go even further to a regime where EF even drops below the bottom of the band. And the question we asked was, can a band insulator become a superconductor? So the question was, if you have a system with no Fermi surface, as for example in a band insulator, how would that develop superconductivity? Okay, so what we have done are some model calculations on this, and we have some very definite answers. I'm going to just give you the basic idea behind that. So if you, let's say, take a site with 2 orbitals and have 2 electrons in the orbital, then essentially what you get is a half-filled band. A completely filled band. So here I have these 2 orbitals on each site, and I turn on some tunneling that gives me these two bands here with these 2 density of states in blue and green. And if I put 2 electrons per site, that essentially fills up the blue band and gives me a chemical potential in the center. So that would be the typical band insulator. As you increase the tunneling, at some point the tunneling becomes on the order of the level, the spacing between these 2 orbitals, and there's a band overlap, and you get a metal. So this is in the non-interacting situation. Now, if you turn on attraction, then what happens is I'm showing that in this picture here. So you have this valence band and a conduction band. You can create 2 holes in the valence band and 2 electrons in the conduction band. Let me call these couperons. We heard about excitons earlier. Those were essentially an electron-hole pairing. Now I'm pairing these holes by themselves and these electrons, so I'm getting these couperons. So what is shown here is the binding energy of these couperons. So initially, the binding energy when the attraction is 0, the binding energy would just be 2 times the energy to create 1 electron-hole pair. But as the attraction is increased, then it's possible, or you can think of increasing the tunneling, it's possible that the 2-particle energy state, the 2-particle binding energy, now becomes lower than the band gap, the single particle energy. So this is the E2p, which is the binding energy for 2 electrons, becomes lower at some point compared to the band insulator. And at that point, you essentially go into a Bose insulator. And so this is the progression from a Fermi band insulator all the way toward a superconductor. You go through these successive crossovers from a Fermi insulator to a Bose insulator, where the lowest energy excitation has a 2e charge, and that's what goes soft at the transition. It then goes into the superconducting state, but when it just enters the superconductor, it's a Bose-Einstein condensate. And then with further increase of the tunneling, it goes into a BCS superconductor. And the way we can distinguish these 2 is by looking at the location of the minimum gap in the location in momentum space where the minimum gap opens. So in a superconductor, in the BCS regime, you know that at KF, if you follow the gap contour, it's essentially at KF, and you get a closed contour. Whereas in the BEC regime, the minimum gap occurs at at the gamma point, so to say. So there's a change in topology of the minimum gap contour. So the last thing I want to say is, now we understand what a trivial band insulator does when you turn on attraction. What does a topological insulator do when you turn on attraction? And the main question is the superconductor that you get also topological? And what might be the role of the Berry phase? So this, in a way, connects a lot with Tony's work on helium-3. We heard some of about this earlier from Jim Sauls. And let me just say very quickly this is still ongoing work. So we are looking at graphene. There's really no getting away from graphene today. It's become a paradigm for several phenomena. So if you look at graphene, you can see that it has these K and K prime points, these Dirac points that are protected by inversion and time reversal symmetry, and you can break them in two ways. This is just by putting some sublattice potential, which gives you these red and blue are essentially the Berry curvatures at these K and K prime points, and they have opposite Berry curvatures on these K, K prime points. But you can also break it by breaking time reversal invariance, and then you get a Berry curvature which is the same on all the points. So that's like a Chern insulator. And if you take two spin species, then you can have a Chern insulator which does not break. You can get a Chern insulator for spin up and for spin down, so together they don't break time reversal invariance. So in this way, what you can do is go from a trivial insulator, turn on spin orbit coupling, and get into the topological insulator. So this is the band structure level. And now you can ask what happens when you add attraction. And that is, I will just leave you, this is my last slide. This is ongoing work which shows that the phase diagram is really rich. So this is the behavior I just showed, trivial insulator to topological insulator. When you turn on nearest neighbor attraction, it gives rise to a whole lot of superconducting phases here. And among these, they have different pairing symmetries. And among these, we find a topological insulator right there in the middle. So I'll stop here just by, with this last slide and say that, Tony, happy birthday. Graphene is going to be the next exciting physics, especially interaction effects in graphene. The magic angle bilayer graphene is extremely exciting because it's close analogy with high Tc, and this is my happy 80th birthday. Thank you.
So, this may be getting into the engine inside the Chevrolet, but we're told not to do that. But what is your thought about your mechanism for your negative view of your attraction?
Well, I actually don't care, but it could be, so the point is you could even take conventional phonon mechanism. And, so the main point here would be take even something like niobium nitride, right? That's a good S-wave superconductor where the mechanism is just phonons. So it's a BCS superconductor if it is clean. But now when you add disorder, that BCS superconductor will go into a non-BCS regime. So just because of disorder.
So negative view just to allow you to model it simply.
Yes, yes. So another point to make here is, the negative U is an on-site attraction. But if that value of U is very small compared to the bandwidth, the Cooper pairs can be extremely large. So it can model the BCS regime by appropriately taking these parameters.